The priceless feature of the always-on mode of the first-person shot device is being capable of capturing the most artless and valuable moments, for example, the first rolling of the baby during a day at the park. However, this extremely short moment happens in a very long video, most composed of boring and monotonous moments, such as the 30-minute driving and the picnic setup. The main motivation of semantic hyperlapse is to provide a visualization of the whole video story, emphasizing the relevant moments. The application of simple hyperlapse techniques could literally remove a relevant event, since they could occur in a flash. The bigger difference from summarization method is the fact that the semantic hyperlapse create visually pleasant videos displaying all the events that occurred, while summarization only returns clips of important moments. Most of hyperlapse techniques model the adaptive frame sampling, searching the optimal configuration in the feature space. The drawback of this approach is the non-scalability in the number of features once it exponentially increases the computational time and memory usage. In this work, we present a new semantic fast-forward method that solves the adaptive frame sampling by modeling the frame selection as a weighted minimum sparse reconstruction problem, guaranteeing feature scalability and time efficiency. In the proposed methodology, given an input first-person video and a defined semantic information, a relevant score is calculated for each frame of the video, generating a semantic profile. Following, the video is segmented according to the frame's relevance, and speedups are calculated in a way that the most relevant parts are emphasized by applying a lower rate. For each segment and its respective speedup, we model the adaptive frame sampling as a weighted minimum reconstruction problem. For each frame, a high-dimensional descriptor is extracted, characterizing the movement, visual appearance, content, and temporal sequence in the video. The dictionary D is composed of the descriptors DI of each frame, and the video representation V is defined by the sum of the frame features of the whole segment. As specified in the LLC formulation, the vector G is the Euclidean distance of each dictionary entry to the video representation V. We added a weighting term W to create a more robust solution concerning the camera movement. To estimate motion segments, we use the cumulative displacement curves generated from the sparse optical flow. Camera motions are identified when all curves present the same behavior. A lower value is assigned to the weight related to frames into the motion segment. The frames related to the activated position will be selected to compose the fast-forward version. The speedup of the created video will be defined by the sparsity of the solution vector. Using the lambda value as 0 leads to selecting all frames once the sparsity term is disregarded. We search for the correct value iteratively until it converges to the required number of frames in the accelerated video. The solution of the minimum reconstruction problem does not ensure a final, smooth, and continuous fast-forward video. Since the idea is to reconstruct, the solution might oversample in a high-detail segment and ignore visually similar views. To address this issue, we propose a smoothing transition process. The first step is to perform the sampling using fewer frames than the required. Following, we identify the transitions with highest view dissimilarity. Then, a new frame from the original segment, which best smooths this transition, is chosen to compose the video. The process is repeated until the required number of frames is achieved. The proposed weighted sparse sampling is applied to all segments of the video. Finally, the fast-forward versions of each segment are joined, and a stabilization process is performed, creating the final fast-forward video.